Welcome to Obhi's Math e-Pathshala. Today's topic is finitely generated abelian group. So, finitely generated abelian groups. Yeah. Now we shall start by introducing additive notations. Uh, Additive notation in an abelian group G, which is as follows. So if we consider an abelian group, then we will introduce the additive notation for the binary composition actually, and for that reason we need to denote. So it denote the identity element as 0, element of G as 0. We denote by Na equals to, what is Na? Na is a plus a n times minus Na, that is minus a n times, and 0a is 0, where this 0 is from the integer set 0, and this is the identity element of 0. Okay. Hello. Okay. So now, but we shall continue to use the we shall continue to use cross for direct product of groups. So we shall continue to use cross for direct product of groups. Okay. Now recall that if we consider the group Z cross Z, then Z cross Z is a torsion free group. Torsion free group which is generated by the set 1 0 0 1, as for any I comma j belongs to z cross z, we have I comma j equals to I of 1 0 plus j of 0 1. So in this way we can show that z cross z is generated by the set 1 0 0 1, that is this set 1 0 0 1 is a generating set of the group. So this is the generating, so this is a generating set for the group z cross z. But it is to be observed that each member of z cross z can be expressed in the above way, this one, uniquely. That means I and j both are unique. So this way of representation of any element of z cross z is unique. So this is a special property which this set enjoys. And keeping in mind this property, we are to state a theorem which deals with this property in general. That is, if we consider a set which is a subset of a non-zero abelian group, where G be a non-zero abelian group and X be a subset of G, then the following are equivalent. Then the following are equivalent. Number one is each non-zero element X belongs to G can be uniquely expressed in the form X equals to n1 x1, n2 x2, nr xr for n is not equal to 0, for at least 1 and xi's are distinct elements of X. Okay, this is the first statement, and this is on the second. That is, X, this set X, it will generate. So it generates the group G. This is the first property, and in addition to this, if n1 x1 n2x2 plus nrxr. If this is 0 for ni's are in z integers and distinct xi's are from x, this will be if and only if all those integers are 0. That is, if n1 x1 plus n2 x2 plus nrxr is 0, if and only if n1 equals to n2 equals to nr equals to 0. So these two statements are equivalent to each other. That is, if 1 holds, then it will imply 2 and 2 will imply 1. And the proof is very simple. So let us first consider the case when 1 implies 2. Now we have assumed that G is a non-zero abelian group. That is, G not equal to 0. So it is not trivial group. It is a non-trivial group. Okay. And X is also not equal to 0 because of this relation, since 1 holds. Okay. And since so 1 implies that 0 will never be in X. For if some element is 0 and if we consider another non-zero element in X, since X not equal to 0, we have already stated, then you will have two representations of xj. That is, one is xj itself and another one is xi plus xj. So this violates the uniqueness of the expression. For xj. So this implies that 0 will never be in X. Okay. Okay. Now, since we have assumed 1, so 1 shows that the set X generates the group G. Since 1 states that every non-zero element X can be uniquely expressed in this way. So the first one is every non-zero element X can be expressed in terms of xi's, where xi's are distinct elements from the set X, capital X. So therefore, capital X generates the group G. So this one is clear. Now we need to show that if for x1, x2, xr, if n1, x1 plus n2, x2 plus nr, xi is 0, this will happen if and only if n1 equals to n2 equals to nr equals to 0. So we need to show this one. So shows that X generates the group G, and of course N1 x1 plus N2 x2 plus NR xr, if this is 0, this is 0 if we consider N1, N2, NR, each of them is 0. So this is trivial. That is, if they are 0, then this expression must be 0. So let us consider the reverse case. That is, suppose N1 x1, N2 x2 plus NR xr, it is 0 with some Ni not equal to 0. Let us suppose that some Ni is non-zero. We need to show that every Ni is at 0, but we are considering that, okay, some Ni is non-zero. So definitely it will contradict our assumptions. So then we see that x1 can be written as x1 plus 0, and x1 plus 0 is n1 x1, n2 x2, nr xr. So this implies, so it will be n1 plus 1 x1 plus n2 x2 nr xr. So you see that x1 has two expressions. One is x1 itself, and another one is this n1 plus 1 x1 plus n2 plus n2 x2 plus nr xr, which, so this gives two ways of representation for x1 not equal to 0, which, and this leads to a contradiction. This leads to a contradiction, and hence our assumption was wrong. That is, some Ni is non-zero. This is wrong. So hence every Nk is 0 for all k 1 to r. So this proves that 1 implies 2. Now we move to prove that 2 implies 1. So let us suppose that x belongs to G, and since we have assumed that x generates the group G, so therefore, since x generates the group G, so x can be written as, expressed as some n1, suppose x1, n2 x2 plus nr xr. But we need to show that this way of expression is unique. So suppose that x can be written in another way also. So suppose that x has another representation. Which is x is m1 x1, m2 x2, ms xs. So So this implies, so these two expression will imply that m1 minus n1 x1, m2 minus n2 x2, mr minus nr xs xr plus mr plus 1 xr plus 1 mr sorry ms xs 0, where we suppose that s is greater or equal to r. So by 2 we can say that all these integers are 0. So m1 equals to n1, m2 equals to n2, mr equals to nr, and others are 0. Right? Okay. So this proves that the coefficients are unique. So this proves that the coefficients are unique. So actually someone may ask that how do you know that this x1, x2, xr will be the same for two representations? The way is that if we consider x is, okay, suppose x is n1 x1 n2 x2 and nr xr, this was the first expression, and if we consider the second one is the like that, m1 suppose some x k1 m2 x k2 mr ms x ks. So these elements are maybe different from x1 x2 xr. Let us suppose that, but we can express x as n1 x1 n2 x2 nr xr, okay, plus for these elements we will put 0, that is 0 x k1 0 x k2 0 so 0 x ks, okay, and for the second one we will put 0 for these elements, that is x1 x2 xr, that is 0 x1 0 x2 0 xr, and others are m1 xk1 ms xks. So we will add all these elements, that is we will consider all these x1 x2 xr xk1 xks together and renaming these elements as, suppose, x1 x2 xs. So for that reason we have considered this x1 x2 xs. Okay.
Thanks for watching. Please like, subscribe and share, and drop your comments in the comment box.